So, guys, this kind of comes as a congratulations and not a condemnation. You guys are generally amazing at monitoring your time and going, yeah, we'll get done, or no, we should stop. And we have those conversations a lot. Obviously, we didn't do as well today, but the fact that this is the first time this has happened to us is kind of amazing and great. Normally what I'd like to do is just be able to say, hey, let's just finish up this lab. Let's push today into next week and lecture. But guys, from looking at the calendar, you understand that if we do that, the dominoes start to fall, right? And then we don't finish all of the material before the spring break and things just get weird. So guys, we are going to push through. We weren't going to grade homework today anyway. You'll see why. Partially it's because this homework goes on next quarter's grade, and Skyward gets grumpy when I try to do that before it's fourth quarter. But guys, the other reason is because the conceptual stuff is actually where we're going to start right now. And so consequently, it works to just, and we will, after the weekend, we'll look at this homework, but we weren't going to grade it today, even had we not ran short on time. So guys, what we're going to do, as it says in the notes, is we're going to talk today about titrating buffers. So before we get started, are you guys okay? Or are you so freaked out sprinting from there to here that you just need a minute to gather your thoughts? You guys okay? Breathe in through your nose, out through your mouth. Cleansing breaths. Big stretch. Wiggle your butt a little. You guys okay? All right. Hey, so guys, what I want to do to get started today is I want to talk with you again about the conceptual underpinnings of buffers. Then what we're going to do is we're going to step out of that for a minute, and I'm going to ask you to protect what you've drawn by giving it some space, because we're going to come back to it. So we're going to do buffers conceptually again up on the screen. And then guys, we're going to skip down a little bit in your notes, and we're going to talk about the two important factors that you need to keep track of when we're talking about buffers. Then we're going to go back up in your notes, talk again about how buffers respond to acids and bases attacking them. But we're going to change the conversation from conceptual to mathematical. And then once we've defined some mathematical footwork, we're going to start solving some problems about how we describe titrating buffers mathematically. So you'll see, it all fits together well. So guys, with that said, I would encourage you to skip down like 3 lines at the top of your notes. And let's do acetic acid and sodium acetate as our buffer, simply because that's common, it's familiar. So guys, I'm not going to draw a beaker. So we're just going to talk about this sans beaker. So we picture this, and this is vinegar sitting in a jug, right? But vinegar sitting in a jug is not a buffer. So what do we have to do to this to buffer it? Add the common ion, right? The acetate ion. And so we would choose a sodium salt, a potassium salt. Why do we choose those salts? The positive ion doesn't do chemistry, right? So what we end up with then, guys, and you may want to write this in, we end up with a large molarity of this, and importantly, a large molarity of the conjugate base ion. This then is a buffer. And so guys, the idea then is this: we can attack this buffer with acids, or we can attack this buffer with bases. And this is the way we're going to represent this. So guys, if we add an acid to the buffer, what does the chemistry do? It goes that way, right? I like that's a good way to think about it. So guys, what it does is it shifts the equilibrium in this direction. So the negative acetate locks onto the positive hydrogen ion, forming more unprotonated acetic acid molecules. But guys, notice, again, keeping your eye on this, which is representative of pH, that doesn't change. All of the hydrogen ion that we're adding is actually latched onto by the acetate, forming acetic acid, and so this doesn't change. But then, guys, let's remind ourselves, it does change a little, right? Do you remember why? So if this goes up and if this goes down, Le Chatelier's principle says, which way will the equilibrium then shift? A little bit back to the right. And we're going to talk about that mathematically today. But the equilibrium then reestablishes itself, and this goes up a little, but it doesn't go up by the amount of hydrogen that we're adding. It goes up based upon the Ka of the weak acid. Is that okay? Okay. Then, guys, what if we add OH? Well, it goes in the other direction. But remember, what's our additional product? Water comes out of this. And again, guys, the hydroxide that we are adding are not attacking the protons that are in solution. Therefore, the pH doesn't change. But then what happens is, as it reestablishes equilibrium, this has gone up, this has gone down. To reestablish equilibrium, it goes to the left. As it does, this does go down a little. So the pH does go up a little, but not as much as if we were just dumping hydroxide into water. You guys all settled on the chemistry? Okay, so guys, do this then. Skip down 3 lines in your notes. Hold on, let me think. Yeah, 3 lines will be fine. Skip 3 lines in your notes. And guys, we need to step out of this conversation for a minute. And there's a couple things that we need to be aware of relative to buffers. Then we're going to jump back into this conversation, and we are going to talk about the math that describes all of this, and that's going to be the end of our day. Okay, so what are the things that we need to talk about in the meantime? And the guys, the answer is, first of all, the capacity of a buffer. So when we talk about buffers, there are 2 additional things you need to understand, and one is capacity. So guys, when we talk about the capacity of a buffer, and again, as you're writing this down, skip down 3 lines. Guys, when we talk about the capacity of a buffer, we are talking about the amount of acid or the amount of base that a buffer can absorb. And again, as it says in the statement, not again, but as it says in the statement, we mean absorb without an appreciable change in pH, because that's what buffers do. Are you guys caught up? You're okay? So guys, let me turn this to you as a question rather than just giving you the answer. And guys, the question then becomes this. Given what you've got in your notes, what in this scenario would tell you the capacity of this buffer? So guys, the buffer that we drew up on the board a second ago, how much acid or how much base can this buffer absorb? Exactly. Guys, it's a function of the concentrations of the 2 components of the buffer. So the more concentrated, doesn't that make sense? The more concentrated these components are, the more acid or the more base that this could absorb. So capacity is a function of the molarity of the weak electrolyte and the conjugate that you make the buffer from. So the stronger those things are, the greater the capacity of the buffer. So guys, the capacity depends upon the amount of weak electrolyte and salt from which the buffer is made. Which I hope, guys, makes sense logically. So guys, this then brings up an interesting question. And I'm going to ask you not to write it down because you're going to choke on the words rather than getting into the concepts. But are you guys all caught up again? Let me share this with you. So here's an example. And let me zoom into this because it does get a little small. But guys, let me share with you the setups, if you will, for 2 different buffers. So guys, imagine that we have a liter of solution. Doesn't really matter the volume. But guys, we have a liter of solution that is 1 molar in both component, and then we have a liter of solution that is 0.01 molar in both components. Guys, here's the question. Which one will have the greater capacity? Top or bottom? Top. How many times greater? 100 times greater, because the concentration is 100 times greater. Do you get it? Is that okay? Now let me throw you a curveball. What will their pHs be? How do you know? You're right. Yeah, no, you're right. Guys, their pHs are the same. And if you're thinking about it, you should be going, wait, there's no way that that can be the case, because a 1 molar acid would have a lower pH than a 0.01 molar acid, right? So guys, let me turn this off so I can touch my board. So if it was just this, their pHs would not be the same. But when we buffer these with equal molars of our conjugate salts, it turns out that their pHs do become the same, because while this is a stronger acid, it's got more conjugate base, which pushes the more of the acid backwards, and you do end up at the same pHs. So guys, these will have the same pHs. But you learned something last time that actually should have told you that their pHs were the same. Do you remember what you learned? Say it again. Yep. Yes. You got it. So guys, the idea is this. When the molarities are the same, pH is equal to pKa. And because these are both acetic acid solutions, because these contain the same weak acid, they have the same Ka values. Therefore, it doesn't matter if it's 1 molar and 1 molar or 0.01 and 0.01 molar. Guys, if their molarities are the same, then pH is equal to pKa, and because it's the same weak acid, they have the same Ka values, so their pHs have got to be the same. So you saw this mathematically before. Now we're seeing it in a little different context. So guys, fundamentally the idea then is this. The top one will be a better buffer, but their pHs will be the same because pH is equal to pKa if the molarity of the weak thing and the conjugate are the same. You guys okay on those ideas? You're sure? You're good? Okay, so guys, that was thought number 1. Anything you want to talk about there? Okay, so here then comes thought number 2, pH range. So guys, in lab on, just 20 seconds ago, guys, when you were in lab, you know that I cheated, right? I set out a beaker that was buffered at pH 4, and I set out a beaker that was buffered at pH 10. And I didn't mix those solutions. Some of you saw me do it, where I buy these little capsules that already contain the weak acid, or the weak base if it's pH 10, that contain the weak acid and the conjugate salt in the right amounts so that we can actually mix these things, and I just dump it in and swirl it and off it goes. But guys, the question is, what if you didn't have that advantage? And what if you needed to figure out how to make a buffer at any given pH? Do you know what I'm saying? And guys, let me offer you an example. So take, for example, our good friend acetic acid, which has a Ka of 1.8 times 10 to the negative 5th. Yeah? So guys, the question then is, what would be an effective buffer? So if we decided to take acetic acid and make a buffer out of that, would that work well if we needed a solution buffered at 10 or if we needed a buffer at 2 or 5 or 6, or how does this work? So guys, if we wanted to build an acetic acid buffer, what pH range would we expect that to be useful for? And so guys, to answer the question, here's what you do. Take the negative log of that number. Take figure out pKa. And you may want to do this with me. So guys, take 1.8 times 10 to the negative fifth, and then figure out, oh my gosh. Oh, that's what's wrong. Here we go. So guys, I get 4.74. Did you all get that too? Okay, so let's talk about what that means. So if acetic acid's Ka is 1.8 times 10 to the negative fifth, then pKa is equal to 4.74. But guys, what does that tell us about an acetic acid buffer? Tying back to what we just discussed, what does that tell us about an acetic acid buffer? Are you making the connections backwards? So imagine this. I've got to draw a beaker. So guys, inside our beaker, let's say that we have 1 molar acetic acid and 1 molar sodium acetate. What will its pH be? 4.74. Let that soak in. Do you see where this is headed? So guys, we said we were okay with this on the previous slide. If we have 1 molar and 1 molar, or if we have 0.001 molar and 0.001 molar, we agreed that the pHs would be the same, right? And we said that that's because at equal molarities, pH is pKa. Well guys, now we're sticking a number to it. If Ka is that, then pKa is 4.74. So guys, that means that this thing will have a pH of 4.74. Does that make sense? Okay. So guys, what you're going to find out then is this is a strategy that you can use to make buffers. And the logic goes like this. Say that you wanted to make a buffer that has pH 3. Okay? So what would be a logical place to start? Well guys, if you wanted a buffer that has a pH of 3, what you want to do is find a weak acid that has a Ka of 10 to the negative third. Do you get it? Do you get it? Because what is the negative log of that? 3. Guys, this is the strategy that you use for building buffers. What you do is if you want a buffer at 3, you find a weak acid that has a Ka of 10 to the negative third. Then what do you do to build that buffer? You take equal molarities of whatever that weak acid is and the conjugate ion salt, mix them together, and there's your buffer at 3. Does that make sense? You are going to see questions on this on the AP test. You will see a question it's in multiple choice, but you will see a question that says, here's a list of weak acids. Here's their Ka values. If you want to make a buffer at pH 6, which of these weak acids would be the most logical one to buffer? What would the answer be? The one whose Ka is closest to 1 times 10 to the negative 6th. Do you understand the idea? Does that work for you? Okay, so guys, that's the logic that you need to understand relative to this relationship to pH range, is you can pick the components of your buffers based upon the Ka values. Yeah?
So I just have a question about the thing where the pH are the same and the how far down is that?
That's a good question. Wait, what do you mean by down? Maybe I'm not going where you...
How far, how small
Oh. So you're saying I don't know if I can go...
Eventually you could have one hole in the ocean.
Yeah, I get where you're going, sort of. So back here, right? So the idea is, how small can these molarities be and still this relationship holds true? And there's two answers to that. One is, eventually these buffers become practically worthless because the molarities are so small that they don't really function as buffers, because you sneeze on them and they break because of the little bit of acid in your snot. I just kind of made that up. But the idea is, these would have such small buffering capacities that they wouldn't functionally be buffers because they would be overwhelmed so quickly by the external acid or base. With that said, in theory, this relationship, as these become more and more dilute, goes out until you're starting to impinge upon the molarity of the until you're starting to impinge on the molarity of the hydrogen and the hydroxide that's in distilled water, which is 10 to the negative 7th molar. At that point, the acidity and basicity of the water becomes as important as the acidity and basicity of the stuff you're adding, and then it all changes. Is that okay? So guys, go ahead.
So you have like an acid with some pH 3 kind of buffer it.
Yeah.
Or let's say it has like pH of 3.5 and you're trying to make a buffer at 3.
Yeah.
Then could you like add certain things on either side of the equilibrium?
That's a really good question. Let me get back to where we were, and then I want to write down your question, Luke. So you're saying, what if we have an acid that has a Ka of 1 times 10 to the negative third, but we want to create a pH of 3.5, right? Was that your question? However, so the answer is, how could you do that? And the answer, you said add other things. Actually, the thing that you would do would be to tweak the molarity of the conjugate salt. And by tweaking the molarity of the conjugate salt, you could shift that equilibrium enough that you could actually create a buffer at that pH. No. And again, so like the question that they would ask you on the AP test would be like, given these acids and here's their Ka values, how would you make a buffer? Which one would be the best weak acid to use to create a buffer at 6? And so you would pick the one that's closest to 6. They wouldn't then come back and ask you, how much conjugate salt would you need to add if the Ka value is whatever it is? Yeah, no, you won't see that. So, do you guys understand the concept? There's one other thing we need to talk about, guys, relative to this idea of pH range. There is a limit to the thing that Luke is asking us about. So in theory, you can take a weak acid with a Ka of 10 to the negative third, and if you add enough conjugate salt to this, you could drive the pH like crazy. And so where's the limit to that? Where's the, because you've got this balance between weak electrolyte and conjugate salt. At what point do those become so unbalanced that the buffer's no longer functional? And guys, the answer is this. Buffers work best when the concentration of the weak electrolyte and the conjugate ion are approximately equal. And guys, you understand when that's the case, pH is pKa, right? So if the weak electrolyte and the conjugate salt have the same molarities, then pH is pKa. And buffers tend to be the most effective when those are about the same. But there's a limit to about, and that limit is tenfold, or 1 order of magnitude. So guys, if the concentration of your weak acid and your conjugate ion, if their concentrations get different by more than a power of 10, then that buffer tends to be susceptible to breaking, and we don't think of it as being functional. So what that means, though, is that if 10 is the magic number, so it could be, these things could be out of whack where one is stronger by a power of 10, or you could think of it as if the other one is weaker by a 10th. Then guys, the log of 10 is 1, and the log of 1/10 is -1. So guys, functionally what that means then is this, that buffers usually have a usable range of pH that is pKa plus or minus 1? And if that was just a bunch of gobbledygook to you, I'll explain it in just a second. You guys okay? Would it be helpful if I explained what that means? Okay. So guys, the idea is this. Let's go back to this thing that we're saying, where we're saying if we've got a weak acid with a Ka of 10 to the negative third. Guys, if we make a buffer out of that where the weak acid and the conjugate salt have the same molarities, then guys, what will the pH be? Are you guys writing or are you not understanding? Let's say it again. So guys, we've got a weak acid with a Ka of 10 to the negative third. We build a buffer out of that. How do we do it? Well, we add a salt that shares that ion, but we're going to be smart about this and we're going to make the molarities the same. So the idea is if the molarities are the same, then pH is equal to pKa. Therefore, the negative log of that is 3. You with me now? Okay. So guys, what that means is this thing will have a pH of 3. Now, we can change the pH, though, of that buffer. We can make it above or below 3 by changing the relative molarities of the weak acid and of the conjugate base salt. So at this point, as Luke was thinking about earlier, we can start fine-tuning the pH of the buffer by relatively changing the concentrations of the two components. But guys, there's a limit to how much of that you can do. If this becomes 10 times more concentrated than this, or if this becomes 10 times more concentrated than that, at that point, the equilibrium gets so out of whack that it doesn't function well as a buffer anymore. So we know that these concentrations have to be within a decimal place of each other. But guys, the log of 10 is 1 and the log of 0.1 is negative 1. And so consequently, that means that this pH can range from 2 to 4. So when you do this Ka thinking, the idea is there's limits to how far you can stretch that, and those limits are reflective of concentration changes of 10 in either direction, but the log of 10 in either direction is plus or minus 1, and so this pH game that we can play only really works plus or minus 1 to Ka, so this particular weak acid would be an effective buffer if you set it up right from about 2 to 4. Beyond that, it's just not going to buffer well. Does that now make sense? You guys okay? Okay. So guys, this was kind of an aside. Let's make sure you're good on these ideas. So idea number 2, which is just what we went over, is this idea of selectively choosing weak acids or weak bases, but weak things to buffer based upon Ka and the pH that we're shooting for. And then guys, in addition to that, we talked about this idea, which is that buffers have capacities that are based upon molarities. You guys good? All right. So with all of that said, guys, here we go. We are now going to talk about the math of titrating buffers. So go back up in your notes to here. And I'm going to switch to black. Okay. So guys, let's reconnect with the concept of how buffers work. And then guys, let's talk about how we're going to describe this mathematically. But guys, you definitely want to write into your notes what I'm about to put up here, because we're going to take ice boxes and we're going to change them based upon this conversation. So guys, quickly coming back to what we said before. So the idea, guys, you know what? I'm going to start over. Just to get into the chemistry, I'm going to start over. So we've got acetic acid, we've got acetate ion, and we've got protons. And guys, let's do this. Let's add acid to our buffer. And you've already got this in your notes, but let's reconnect with what I'm doing. So guys, you add acid to this buffer. Which direction does the chemistry go? Left or right? It goes left. And guys, understand, when you get to college, you are not going to have professors that teach this to you this way. This is going to save your butt and perhaps get you dates. Because guys, if you understand this, you can actually teach this to your friends and they're going to love you, but tell them that you only explain this to them Friday night over dinner, and that provides dating opportunities. So, guys, it goes like this. Guys, this shifts the chemistry to the left. And your college professors are going to try to explain this to you by doing all this weird, like writing all these different balanced equations. Guys, this is all that's going on. But here's the idea, and this is important. Don't gloss over this. Before we add the acid, this is a bucket of vinegar, right? Realize that we've buffered it, so we've got increased molarities of both of these. But guys, inside this bucket, what's going on? Is there any chemistry taking place? Oh yeah, right? It's an equilibrium system. So these guys are going this way, and these guys are going this way, and they're just hanging out doing their equilibrium thing, and these are happening simultaneously in both directions. But there's chemistry going on. They're going here, they're going there, it's at equilibrium, right? Okay, now guys, here's what, and we should talk about this. Guys, when we talk about equilibrium, what is equal? The rates. So the rate at which this is happening and the rate at which this is rates are dependent upon collisions, and collisions are dependent upon molarity, right? So this is all rate chemistry, this is all equilibrium, this is all molarity stuff doing its equilibrium thing, right? Okay. Then guys, we come in here and we louse up the works. We dump a strong acid in there. Guys, do strong acids do equilibrium stuff? No, strong acids go in there and they start kicking butt. And guys, here's what happens. For every molecule of this that you add, one of these dies and one of these gets formed. Guys, this whole namby-pamby equilibrium game is no longer the chemistry that we care about. Now what we care about is every molecule of acid that we add, one of these dies, one of these gets formed, and if we keep adding acid, these die and these get formed, right? But then guys, what happens after we're done adding the acid? Goes back to equilibrium. Do you get the idea? Okay. Now guys, what about this? What about if pretending we're starting over? So this thing's doing its equilibrium thing, and we start dumping in base. Do strong bases play the equilibrium game? No. These strong bases go in there and they kick butt too. And for every molecule of strong base that we add, one of these dies, one of these gets formed. It also makes water, but let's not worry about it. But guys, again, this is not equilibrium chemistry. This is molecules going in there and beating the bajinkers out of each other. And every molecule that you add, another one dies and another one gets formed. Do you understand the idea? Okay, so guys, why is all of this important? And the answer is this. When we describe equilibria, equilibria is about rate. Rate is about concentration. What are our units for concentration? Molarity. But guys, when we start adding strong acids and strong bases to these things, that ain't a molarity game anymore. This is death and pillaging, right? Every molecule of acid that we add, one of these dies, one of those gets formed. Every molecule of base we add, one of those dies, one of those gets formed. So guys, when we talk about this chemistry, we are counting molecules. And what units do we use to count molecules? Moles. And that's important. So guys, write this down with me. This chemistry right here has to be thought of in moles. Do you see now why I had you skip lines? Guys, that chemistry to be described in moles. Why? Why is that true? Now, that's true, but guys, why does that chemistry have to be described in moles? And what does that depend on? Why is it this is just death and not equilibrium? They're good. They go to equilibrium because they're strong. Guys, because these are strong acids and strong bases and bases don't play the equilibrium game. They play the I'm going to kill you game. And so, guys, this acid or this base is fully reacting. It goes to completion. It doesn't reach equilibrium. So that game has got to be played in moles. But, guys, what about this game? What about the equilibrium game that happens after the strong acid or strong base is done kicking butt? The equilibrium game is thought of in what units? Molarity. Guys, you have no idea how thankful you're going to be that you just drew this in your notes when you get to freshman chem in college. University professors really, really struggle to explain to you what we just drew on the board. Guys, this chemistry happens in moles because it's a strong acid or a strong base. This chemistry happens in molarity because it's an equilibrium process. So now what we've got to do is this, and guys, don't write this down, but let me show you where we're going. You guys are accustomed to describing weak systems, molarity systems, equilibrium systems. You're accustomed to describing those using what are called ice boxes, right? But guys, now what we're going to do is we're going to take this ice box and we're going to stretch it. And when we stretch it, we are going to make room to account for this chemistry. We're going to make room to count for the chemistry of the strong acid or base. And guys, when we do that, our ice box is going to become, and you don't need to write this down now, but we will in a minute together. Guys, this becomes what is called an iRace box. And it goes like this. It's initial, that is how much stuff you started with. Then it is reacted. And when we say reacted, we're talking about this. We're talking about the strong acid or base coming in and kicking tail. So guys, what units are we going to use for our initial and reacted amounts? These are in moles, because this describes the buffer being attacked by a strong acid or base. Then at that point, we are now going to come to our adjusted concentrations. What adjusted the concentrations? The addition of the strong acid or the strong base. And then guys, at this point, once we have our adjusted concentrations, now we're back to icebox. Change and equilibrium. Sorry, I'm getting low on the board. And guys, this portion of this happens in molarity units because now we're describing the equilibrium that gets reset after the acid or base comes in and causes the damage. You guys see how this goes? You okay? So guys, let's apply this. We're going to do this. We're going to go through this slow and together. So guys, it says this. Don't write this down. You need the space. Just work with me here. So it says, a buffer is made by mixing 100 milliliters of 1 molar acetic acid and 100 milliliters of 1 molar sodium acetate. By the way, what's the pH going to be? 4.74. Right, we did the math. Okay, it'll be the same as Ka. the negative log of K. So the K of acetic acid is this. And then it goes on to say this: calculate the pH of the solution after ... We have added 50 milliliters of HCl. So can you picture it? We've got 200 milliliters of buffered acetic acid. Where did I get 200 milliliters? 100 plus 100. So you've got 200 milliliters of buffered acetic acid, and you come along and you dump in 50 milliliters of strong acid HCl. Those strong acid HCl molecules go in there and beat the bejinkers out of that buffer. And then once that's done, we think about that equilibrium being reestablished, and we're going to figure out the pH. You ready to go? So guys, do this with me. Here's how to solve this. First of all, we have to set up not an ice box, but an iRace box. So guys, pause for a second because I have to picture this. So no, I'm good. So, you know what, Nathan, I'm going to try because I want those numbers to stay. So, no, the problem with that is then I wouldn't have record of it and no one else could see it in the screencast. Oh, heavens no. So hold on. So skip a line. So guys, when you do your iRace boxes, skip a line between the R and the A. You'll see why. Okay, so guys, this isn't necessary, but you may at this point find it helpful. In your iRace box, what does the R stand for? Reacted. What is doing the reacting in this example? The hydrochloric acid. That is a strong acid. Guys, that tells you, and this will always be the case, guys, that this reaction has to be thought of in moles because it's a strong acid. It's not an equilibrium process. It is thought of in moles. Then, guys, we've got this, which is the change that reestablishes equilibrium. That is an equilibrium process, which is therefore thought of, wow, that was ugly, which is therefore thought of in molarity units. Okay? Okay, so guys, with that said, we now need to start populating this table. What do we put for initial acetic acid? I'm so glad you fell silent. We have to figure it out. Guys, up until now, it used to be 1 molar because ice boxes are only about equilibrium. But we don't know because we don't need to know the concentration of the acetic acid. We need to know how many of those molecules are floating around ready to die. In this case, they don't die. They actually get friends. But guys, we need to know how many of them there are. So guys, we do a side calculation that goes like this. 100 milliliters, 1,000 milliliters, 1 liter, 1 liter, 1 mole, right? Forgive me for significant digits. So is that 0.1 moles? That's really it, right? Okay. So this is, guys, just let me do that. I'll do it. How many do we need? 3? Okay. Guys, I would strongly encourage you to label your numbers. So we have 1/10 of a mole of acetic acid molecules. Guys, how many acetate ions do we have initially? The same, but guys, not always the same, right? It's the same because this and this are the same. in theory, if you were doing this on the AP test, you would have to do that calculation as well. Now, guys, how much hydrogen ion do we have? Just leave it alone. Don't even put it. Actually, a lot of times I'll just put max. No, that's bad because you'll think that's a variable. Yeah, put a line. Okay. Now, guys, at this point, this is where this arrow drawing thing is going to become wildly important to you. So, guys, it goes like this. Above your equilibrium arrow, if it's an acid, put a proton. If it's a base, put an OH. Then, guys, let's talk about, well, which direction will those protons then push this equilibrium, left or right? Good, 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 good. Okay, so we're going to go this way, right? Now the question is this: by how much? What's the answer? How many molecules of acid did you add, right? Because every molecule of acid that you add, one of those dies, one of those gets made. So we need to know how many molecules of HCl we added. That takes math. So now we go 50 milliliters of acid. Again, the math is a little bit repetitive because of the numbers I chose. Is that right? 0.05? Okay. Now, guys, watch. This is where your friends in college are going to love you. The direction of that arrow that you wrote up above now tells you where your pluses and minuses go. So, guys, what's going to happen to the amount of acetic acid? Does it go up or down? Up by how much? 0.05 moles. Plus 0.050 moles. What about the acetate ion? Down by the same amount. 0.050 moles. Again, protons haven't changed yet, right? Why not? Because what will eventually cause those proton concentrations to change? The reestablishment of equilibrium. At this point, we're doing quantitative chemistry. So now we can do the math. So guys, this comes out to 0.150 moles. This comes out to 0.050 moles. Did I do that right? No? Yes? Oh, I hope I did. Okay. Okay. Now, guys, why did we skip the line? And here's why. So, guys, after we added that acid to the base and to the buffer, after we added that acid to the buffer and the destruction is over, now we have to shift gears in our brain. Because now this buffer, which has been completely violated and messed up, sort of gathers the pieces together and goes, all right, guys, whoever's left, let's go back to equilibrium. But guys, now we've got to put on our equilibrium hats. And if we put on our equilibrium hats, we've got to change units to molarity. But guys, molarity is moles divided by liters. So we need to do a calculation in here that converts our moles to molarities. To do that, we need the volume. What is the volume of what's in that beaker? 250 milliliters. Do you see it? It's the sum of all of the volumes. So we are going to divide this by 0.250 and divide this by 0.250. So guys, that gives us 0.15, 0.25. So really 0.60? Oh, that doesn't seem right. Is that right? All right. So 0.600. What are our units now? Molar. And then 0.05 divided by 0.25 is 0.200 molar. And now, guys, the game changes. Now we're thinking equilibrium. So this is now 0. Now this is going to start to sound familiar. What are these components now going to do? They're going to go to equilibrium. And guys, how do they then get to equilibrium? Well, in order to get to equilibrium, what's going to happen is this is going to go down by x, this is going to go up by x, this is going to go up by x. Why does this not feel right? Have we done something stupid? No. No, not attributed, not yet. Not attributed. This doesn't feel right to me. Yeah. Because, and I'm just thinking out loud here, and because if it started at 1 molar, oh, that's what it is. It's been diluted. Okay, you're right. Okay, so guys, now these go down, and this is 0.600 minus x, 0.200 plus x, and x. Now, guys, stop. I have graded your rewrites of your tests. There is an icebox on that rewrite, right? Guys, even after talking about this rewrite, some of you still got no credit for the rewrite. You're mostly good at setting up iceboxes. But guys, some of you are still struggling with the transition out of the icebox and into the math. So let's talk about what this needs to look like. Guys, we have now established our factors, if you will, that will populate eventually our Ka expression. So guys, at this point, we need to write a Ka expression. So as we solve this, we go Ka is equal to this. Then guys, we need the Ka. We're solving for pH, right? So we need the Ka. 1.8 times 10 to the negative fifth is equal to, so we need our concentration of acetate, which we have said is 0.200 plus x. 0.200 plus x. And then our hydrogen is x, right? And then I think this is 0.600 minus x. Is that okay? Okay. So now, guys, at this point, still closing in on pH. What's our next step? Squiggly dude is 0.200x divided by 0.600, right? Because those pluses and minuses, plus and minus x's are insignificant compared to the original concentrations. So then, guys, we have 1.8 times 10 to the negative fifth. Multiply that by 0.6. Divide that by 0.2. And I get x as 5.4 times 10 to the negative fifth. Can you confirm that? Okay. Guys, let's pause again for a moment, please. I know that this is not where this problem is headed, but some of you still screwed this up on the test. So guys, imagine if instead of saying, what is the pH, the question was, what are the molarities of all of these things at equilibrium? Hypothetically. So if the question said, what are these molarities? Well, how would you figure that out? Well, you would take this number, 5.4 times 10 to the negative fifth, and you would plug it in for x. So 0.6 minus that would give you that one. 0.2 plus that would give you that one, and then it is that. But you need to show that math where you're saying the concentration of acetic acid, 0.6 minus, show that work. So guys, again, that's not what's asked for here, but if that was the case, you need to show those calculations. So again, when you get your tests back, your rewrites, they'll be next week. Guys, if you see you're getting those wrong, you're not communicating your calculations. So with that said, we're here, and so then we can go pH is equal to the negative log of hydrogen ion is equal to the negative log of 5.4 times 10 to the negative fifth is equal to 4.27. So guys, let's error check here. Is this a reasonable answer? What would a completely unreasonable answer look like? Greater than 4.74. Think about that. A completely unreasonable answer would be greater than 4.74. How do I know that? Because if these are equal molarities, pH is equal to pKa, and we've already established that the pKa of acetic acid is 4.74. So I know that's where the buffer started. And if I'm adding acid to it, it's impossible for the pH to go up, right? So the fact that my number is less than 4.74 is initially comforting. But guys, you'll also notice that it's not much less than 4.74. That's what buffers do. Guys, if you had dumped that acid, 50 milliliters of 1 molar, if you had dumped that acid into water, the pH would have fallen off the table. But because you're dumping it into a buffer, the pH doesn't change much, as represented by that value. Do you get the idea? You see how these work? Yeah? Yeah, there is, but its concentration we don't need to worry about, because you're right that water's in the background and it's doing its thing and the buffer's generating a little bit of hydrogen. But, whoa, I just pulled the tip out of my pen. But when we get to the chemistry and the description of the chemistry, you're right that there is a little bit of hydrogen there. But we can really think of this as if the equilibrium starts anew at this point. So you're right that there's some hydrogen there, but that hydrogen actually is coming and going as this takes place. And we should say this. Here's the reason this doesn't, here's the reason why what I just described to you is a little oversimplified. So what we've said is this. We've said, here's the buffer, dump in the acid reacts with the buffer, and then it goes back to equilibrium, right? Those things are happening simultaneously. Adding acid, the buffer is always trying to get back into equilibrium. So in fact, this concentration of hydrogen is always correcting as we're adding acid to the buffer. So it's not like the acid gobbles the buffer and then it goes, okay, now I go back and describe it that way. Because this simplifies the math. But understand that that's not really what's happening. As the acetate is being converted to acetic acid, all the while this hydrogen ion concentration is ever increasing, because 1,000 of these get made, one of them converts back, and so they're really happening at the same time. So we don't describe it that way because the math will get wacky. We think of them as step 1, step 2. And because of that, we don't think about the hydrogen as being created, because we just describe all of the equilibrium resetting at the very end. Is that okay? Yeah, why isn't there some there, right? And there is. But again, we're not, we could do this. We could track it through. It would have to be a video rather than a picture. But you could do this, and you could track this, and you could say how much hydrogen, and then you could add some acid, and you could watch that change, and you could watch that change, and you could watch. But we just basically say, let's ignore this from now and deal with all the change at the end all at once. That's really what we're doing. So. You know what we should do is we should actually go build this in lab and hook a pH meter in it and go titrate it. Yeah, it'd be interesting to see. So guys, you good with the ideas? Does this sit okay? Let me ask you this question then. Let me see if I can get rid of the black. Good, okay. So let me clear this out, and then let me ask you a follow-up question. Guys, what if we reset the buffer, and then what if we came back and titrated that buffer with 50 milliliters of sodium hydroxide? How would this be different? Which two? So instead of H, this would be OH. Then what would happen? The arrow would go in the other direction. What would that change? This would become a minus, and this would become a plus, and all the math would flow from there. You get the idea? There you have it. Okay. So guys, with that said, here's your homework.